Guys. Okay. Are there? We have a little bit of time before we get started. Are there any comments or questions? Any questions or comments about the class homework or lectures? Okay, then I'll be back in a few minutes and we'll start the lecture. Okay, guys. I hope can you guys hear me? Sounds great. So let me switch over to the document camera. So the goal of tonight is well, continue what we've been doing. So what we're talking about is we're talking about the definition of the Lebesgue integral. We talked about a random variable expectation where x goes from omega into say into r. Right. So what we did last time was last time we considered x positive, so x going into the non-negative, and we defined the expectation of x. Right, so this is the definition sign. This was the supremum of expectations of random variables y when y is non-negative and less than x, and y is simple. This was the Lebesgue, the definition of the integral of x. Some of you have pointed out that it doesn't look like an integral, it looks like an expectation. Yeah, so expectation and integrals is tomato, tomato. Probabilists, they don't write integrals so much, they write these expectations instead. And also what it means to be simple. So recall also that y is simple if I can write y as a finite sum of some constant times the indicators for some disjoint sets. So where so yi they're going to be positive constants. M is a natural number. The AIs, they're going to be measurable. AI intersection with AJ is empty for any I not being J. And and so we have an expectation here of a simple random variable. And we also recall that for such a random variable, the expectation, this EY up here, this is simply given as nothing else than summing up over M, YI, and then the probability of AI. So the bottom part here says that if you have these simple random variables, that means you have this finite sum. If you have a finite sum, this here is the definition of such an expectation. And then the general expectation, well, what you're going to do is you're going to maximize expectations of random variables that are simple and that sit below x. So this was this is what we talked about last time. Those of you that were in office hours earlier today, we talked about it during the office hours too. This was the case for positive or for non-negative random variables. So the first thing we need to do is to expand it into R. Okay, so the way that we're going to do that is question in the comments. I'm not sure what this means. There was a 333. Yeah, okay. I'm not sure what that means, but okay. So the general case, so that is when x is positive. That's when the positivity is replaced with real valued, and the way we do that. So we're gonna for a number in the real line, we'll have that x is equal to x plus minus x minus. Right, we have talked about these. Plus functions and minus functions before. So we have this, and if I take absolute value of x, then I get that this is x plus plus x minus. And so this decomposition here, it is this decomposition here that we're going to be using to get the general case. So we write, so for x going from omega to r, we write that x is equal to x plus minus x minus, where these two guys, x plus and x minus, they are now positive. So then we know, because they're positive, we then know, so we know how these two expectations are defined. We know how these are defined, because this is an expectation of a positive random variable, this is an expectation of a positive random variable, and these two, they will fall right into, they'll be covered by this definition here, because I do have positivity. Okay, so then how would we use these two? How would we use these two to get the expectation of x? Well, given that x is equal to their difference, the natural thing to do is to say that then the expectation of x is going to be the difference between these two. And the problem with that is, as we saw last time, is that these expectations, they can be potentially plus infinity. So we have to be a little bit careful about looking at the difference. So provided that the expectation of x, positive part, is finite, and provided that the expectation of negative part is finite, we define the expectation of x as what? As the difference. Well, there was a question up here, what is x minus? Well, so we have, if I take, maybe we should just look at some examples. Right? So if I look at, if I take 3 positive part, I'm going to get 3. If I take 3 negative part, I'm going to get 0. If I take, oh, this should be outside. If I take 3 negative part, I should get 0. If I take minus 3, take positive part, then I get 0. If I take minus 3 negative part, I'm going to get 3. So you see in particular these rules over here, they hold. So minus 3 positive part, minus 3 negative part. This is 0 minus 3. This is exactly minus 3 that you have in here. And the same thing, if you take absolute value of minus 3 is 3. This is exactly 0 plus 3. So we have this condition. So if both the positive part and the negative part are finite, we can look at the difference, and then then the expectation of x is simply just going to be the difference between these two expectations, each of them being defined as what we had before. Right, and when this here holds, this is the same. This is exactly using the second property over here. Maybe it's a little lemma. Lemma, maybe it's just an observation that the expectation of x plus is less than infinity and the expectation of x minus is less than infinity. This happens if and only if the expectation of the absolute value is less than infinity. And when this happens, so when that holds, I should say in which case, we say x is integrable. Right? And this was what you had in your first homework. You have to be able to take absolute value and integrate and get something that's finite. When that happens, you say x is integrable. So this is the general definition of this is the case where this is the case we'll be needing where you have a random variable, so it's a measurable function, and we can define the integral of the positive part, integral of the negative part, provided that both of them are finite. Well, then you can look at the difference, and that difference is going to be exactly the expectation of this random variable that we're interested in. Are there any questions on in this first part here? So I get it, this looks fairly abstract. Maybe we can try to link it to something that is a little bit more familiar. So try to link this to a, so we should have that that this expectation agrees with the expectations you've seen before. Right. So, for example, that when x has a density, f, we should be able to write this expectation. We should be able to write this expectation, or even more generally, no, let's just write x here. We should be able to write this expectation here as an integral over r of x of f of x dx. Or more generally, this is what you're doing in your current homework, that if I take a function, g of x, so g is just some function that goes from r to r. So take a function g like the one you had in the current homework. This is like a hockey stick. It's like I think it was ex minus k positive part, something like that. This is what you have in your current homework. There's maybe a sigma up here too, sigma there. So you take a function like this one. I want to compute the expectation. How do you do it? Well, it's basically what you have up here. You just have to use the function g as well. So you have g of x here, then you have f of x, and then you have dx. So these formulas here, when you have a density f, these should be familiar to you guys. What we have now is a very abstract definition of this expectation that does not rely on having access to a density. So we should have that, however complicated this definition here is, it should be such that when the random variable x has a density, this expectation I got myself created here should be computable exactly as you're used to. Okay, so we should be able to justify that. And how do we do that? Well, if you look at, so these are special cases. So these formulas, so these formulas that have here star, these formulas in star, here are special cases of what's known as, so this is called the integral transformation theorem. And if you look back, at some point, you have probably seen something. What could it be? Something like you've probably seen integration by substitution. You've probably seen integration by substitution. You've probably seen something in higher dimensions, something about a Jacobian. This often happens with polar coordinates. Right. Sometimes, have you guys, are we all good on, have you seen stuff with polar coordinates?
Yes.
Okay, so I hope we're not scared away by so what we're doing here is, in these examples, when you do these types of integration, you're moving away from integrating over, say, so there's a function and you're integrating over the domain, and then you move over and you integrate over the codomain, or vice versa. This is what happens when you integrate by substitution. You're replacing a variable by a function of that variable. In polar coordinates, I always forget how it is. Polar coordinates, this is, how is it? So you're thinking about a vector. So you're thinking about a vector that you call like, or like A. And so instead of thinking about it in this standard basis vector, or in the standard basis plane, you think about it in terms of angles. And then you think about it in terms of length. So you take a point in R2, you can describe it in terms of the standard basis, A and B, or you can describe it in terms of an angle and then a length. So what you do is you basically map this plane R2, you put this into a bijective. There's a bijection into, so the angle will live between, so you have here A and B. This is in R2, you put a bijection between that, and then your theta is going to live between 0 and 2 pi. And the length, this is the, I don't know what you call that. Maybe we should call it the length of Z. This is something that is arbitrarily long, right? So you're moving from R2 into another product, the product 0 to 2 pi cross 0 to infinity. And so you can integrate over here in R2, or you can integrate over this this product over here. And there's a relationship that will take you from integrating over here to integrating over here. And this is where the Jacobian comes up. You always have to make sure that you get this, you get the measure. This dx has to be corrected appropriately. So if you do the polar coordinates, it always comes out to be something with r. This is the Jacobian. And that's because the polar coordinates, this has to do with sine and cosine and so on. We're not going to revisit all that because I'm going to do it in this more general case. But you've probably seen this. So for us, we're having a random variable, and the random variable has domain omega, and we'll take values over in R. Right, so the integral transformation theorem, this says that, well, I have an integral here, my expectation, some people like to write this as an integral over omega of, and then I'll have x of omega, and then I'll have a measure. I want to move this and start integrating. Instead of integrating over the domain, I'm going to integrate here over R. So I want to have that this thing here, instead of integrating over omegas, instead of integrating over R squared, I can integrate over these sets. So instead of integrating over omega, I want to be able to integrate over R. And then there's a good question. So what should I put here? Right, I cannot have omegas. They live in over here. Right, you live that little omega, something that sits in here. I want to have something here with x. And then I need to integrate with respect to something. I need to put d of something here. What should I put here? All right, that x here, this is to be thought of as x of omega. So for us, this is the situation we have. Instead of integrating over the domain, we want to integrate over the codomain, because over the codomain, this is back to R. This here is what we're used to. This is what we know from calculus. Right, and that's exactly what we're finding over here. We're finding that the thing that I need to integrate with respect to, this is this f dx. Right, that apparently is what has to go here. This d over here, this has to become f of x dx whenever x has density little f. But we're making no assumption at this point that x has a density. Right, so we cannot just write a density here because we don't have enough assumptions on x. At this point, x is just an arbitrary measurable random variable, and if it's something like a coin flip, there's going to be no density. So we cannot write a density at this point. We need to figure out what to put here. Okay, so this is what we're going to start out by figuring out. So we should know, so not all random variables have a density. But they all have a distribution. You all have a distribution. So we're used to seeing distributions being, what should we call them? We call them f. Right. F of x, this is the distribution function. This is defined as the probability of x less than little x. You all have a distribution. And so again, x here, this is what happens over in the codomain. This is a value over here in R. So you all have that. So just if furthermore we'll have that f of x can be written as an integral from minus infinity to x of f of y. X also has a density. Okay, so but we're not making this assumption in particular. Our coin flip case, is an example of a random variable that doesn't happen. So we need to figure out what to put over here. And what we're going to be putting over there is this f here. So some of you might have been to office hours, and I think we had a discussion about this maybe a week ago. One can generalize this definition here. One can actually write instead of f of x like this, we can generalize. So let me call this double star. We can replace double star by f of b, which is the probability that x belongs to b, for a set b in the Borel sets. Right, and then we get the top formula. Then we get, so we get double star back from the set being minus infinity to x. Like if I take this set in my definition here of f, I'll get, if I take that particular b and plug it into this formula, I'll get exactly what I have up here. So what we'll have is, so this is just another little observation that at f here, this is a probability measure. Right, so just to check it, it has to be that if I plug in r, I'm going to get 1. But if you look at what we have, p of x in r, this is really 1. So that's true. And you can do the same thing if I take disjoint sets. Maybe I should just do it with 2. If I look at f of A union B, A and B are disjoint, this would be the probability that x belongs to A union B. Right, so we have 2 sets. This here is my picture of R. I have A here and I have B here. Don't mean to indicate that they take up all the space, but I have 2 disjoint sets. What is the probability of being in a union? Well, this is going to be exactly the probability that x is in A plus the probability that x is in B. Right, this here is where I use that A intersection B is empty. Right, and then I get that this is f of A plus f of B. And this can be extended to countable unions as well. But what it means is that f is indeed a probability measure. So we can talk about, so we can integrate, with respect to f. There is a probability measure on R, so there's an integral. Just as there was an integral of x with respect to p, there's going to be an integral of functions that go from R to R, right? So now my domain is going to be R. I can integrate with respect to f. I can write integrals like, right, so instead of omega here, I'll now write where f lives, this lives on subsets of R. Then I'll have functions, we call it for g, and then I can integrate, typically we call the dummies in R, we call them for x. Then I can integrate with respect to f of x. And now you can see why it starts becoming, it's starting to look a lot like what you're used to from calculus, because if f has a derivative, how would you get the derivative over here? If you compute the derivative of f, capital F, or compute the derivative here, and you've seen that in the homework, that at least when little f is continuous, right? If you have this formula and you compute a derivative here, you're going to get exactly this integral here on the right-hand side evaluated at x. This was one of the problems in, I think, the very first, or maybe the second homework. I think the very first homework where you had something with Leibniz rule, so you would have to, in that problem, it was more complicated. You also had an x inside f here. Okay, here we only have an x up here, so you compute the derivative, you're going to get that function evaluated up there. Right? So if you look at the formula we have here, if f has a derivative, f prime of x is equal to f of x, you can kind of see what's going to happen here. you can see that this df here, this is going to be exactly that derivative. So you're going to get g times f times dx. But this is what we wanted. That was the formula that we had in the very, very beginning, and that you knew with what you had seen before.
Wait, so d big fx is the regular expectation?
Well,
formula?
this is we have not proven anything yet, but you can kind of see that this df of x, if I take the derivative with respect to x.
Oh, you move it over. Okay, yeah.
This is f here, right? And then you move the x over
Yeah.
here and you put it in here instead, right? So then this term here becomes fx dx.
Yeah.
So that is exactly what you've been used to. Right, so it's not that far-fetched. we of course we haven't proven anything, but you can see the notation and so forth. It lines up so that it's kind of bound to happen that you will have the usual theory as a special case. Okay, so let me write down the integral transformation theorem so that so we have it under our belt. So this is the theorem. This is the integral transformation theorem. Right, so it says let G go from R to R and be measurable. So I should say for L measurable. And we always need to have integrability, otherwise I cannot talk about the expectation. So I need to have that the expectation of absolute value of g of x is finite. You always have to have that, otherwise the expectation of g that is without the absolute values is not going to be well defined. Then the expectation of g without the absolute value is going to be an integral. So here we're integrating over omega. We're going to transform the integral to being over the codomain of x. So this is going to be an integral over r of g of x here, and then it's going to be this df of x. And so if there is a density, this is if so this is a big if there is a density, then you can write this as an integral over r of g of x, and then you get f, so this is my density. And the way that the proof goes, I'll do maybe the key step. It's a step-by-step approximation, just as we talked about last time. When you work with the Lebesgue integral, it's all about chopping off the y-axis first, and then subsequently use that chopping off to chop off omega. And this is the same thing that's going on here. So the first step is you consider the indicator case, which is what we have had before. So you look at g of x to be an indicator. So this is the indicator of a set B of x. And so this is, remember what this means. It means that it's 1 when x is in B, and it's 0 else. And B is a broad set. So we start out by proving the formula for this guy. Okay, so let's do that. Let's work out what the left-hand side is. So we're going to take g of x. Let's work out what it is. Like, I want to prove that for this particular kind of function, for this particular kind of Borel measurable function, I have the conclusion. So I'll do this first, and I'll plug in what is the definition of G. Or is this indicator? So this is going to be the indicator for the random variable x being inside B. But I know what that is because the expectation of an indicator, this goes all the way back to how we had originally.
Is it the probability?
Yeah, that's exactly it, right? It goes all the way back to how we had defined the expectation of an elementary or simple random variable. The expectation of such a y, it is just the sum of the yi times the probability, right? So the expectation of an indicator, this is the probability of the set. So this here is the probability of the set. This here is P of x in B, which we know what is because that was our distribution function. This here was my f of B. Right, so this expectation in the particular case of an indicator is going to be f of B. So that was the left-hand side. So now we have the proof that the right-hand side is the same. So let's work out what the right-hand side is. The right-hand side, so this is the integral over R of g of x df of x. So what is that? Well, g was the indicator, so g is equal to 1 on B, and is equal to 0 else. So I just need to integrate over B with respect to the measure f. But that is exactly f of B. So the two things coincide. This is the same as that. Therefore, this mess is the same thing as that mess.
Professor, the F is the probability measure?
Yes, right? That was what we just had. F is a probability measure.
And that's distinct from and the P is a function that takes the omega into R, and that's why it's.
P is also a probability measure, but they're on different names, right? P lives on omega, F is on R. Right? This measure P here works on the sigma algebra F. And F.
Oh, wait. The P works on the sigma algebra. F.
Yes.
And is that this? That's not. Is that the same F here or a different F?
I'm not sure what you mean.
Like we're using F as a probability measure.
No. So.
It's like the bold F, right?
So we have our omega FP, right?
Right, yeah.
P is a probability measure on F.
Oh, and F is our sigma algebra.
Yes.
Right.
We also have R, P of R, and F. And here F is a probability on B of R. Right, these are subsets. These are subsets of omega. These are subsets of R. Right, and you're linked by this random variable that goes from that space into this space. I get f by transforming p with a random variable x, right? And the way that I do it is by saying that f at a set b, this is nothing else than measuring the probability that x belongs to a set b. Right? Remember, this is shorthand notation, right? This is nothing else than sloppy notation for these omegas in omega for which x of omega belongs to b.
Oh, so we're saying that those probability measures are actually equivalent, like the P and
No,
F.
no, you live on different spaces, right? Omega, this is where you find p,
Okay, right.
and f, this is something that lives on r. They're not equivalent because they live on different spaces.
Okay, but why do we have the f of b defined as the p of? Oh, I guess it's an image. Then.
Yeah.
So
So
that's why.
right, this measure here, it lives over on the image, and p lives on the domain.
Okay. Got it.
Okay. And so now what we're trying to do is we're trying to replace integration over omega with integration over r. And the reason we want to do that is because integration over r, this is something you guys are familiar with. Whereas this abstract integration that we've been doing, this is something that is new and complicated. But if I can somehow push this integration theory to the background by establishing that instead of integrating over this abstract set omega, we can transform everything and perform the integrals that we need over r, and thereby reuse all the machinery that you have learned in calculus, then we can kind of cut a corner. And that's what I'm trying to do with this integral transformation theorem that allows us to move integrals over omega to integrals over r. Does that make sense?
Yeah.
Yep. Okay. So what did we get to? We got down to a special case. Maybe we should just call it quits here with a special case. This was like a special case. So then step 2, you do the same thing as what we did with the. So now we have it for an indicator. So the next step is to use to extend it to G's that are a little bit more general than these indicators. So the ones that you're going to be looking at will be like finite sums of constants times indicators for disjoint sets. So you have constants, say they're positive, and then you have disjoint sets. So you have Borel sets that are disjoint. And you get it to work there. The third step is limits. This is where you always use monotone convergence. And you use the splitting that we also talked about last time. We look at these sets, I think we call them BINs. These were these sets where you look at I divided by 2 to the n. So you look at G's that are in between here, and then you let I run from 0, 1. I think we had it running up to n to the 2nth. Probably -1. And then the last step is you do this, you do the difference. And so the last step is you look at, you decompose, because here we have positivity. So you decompose into these differences. The key step is really to get it to work for these indicators. As soon as you have it working for the indicators, then you can form linear combinations. And if you can form linear combinations, you can start taking limits of these linear combinations. And if you get it to work for these limits of these linear combinations, you can look at differences. If you can get it to work for each component, you can get it to work for the difference, provided that you don't get explosion to plus infinity. And that's how the proof goes. So this establishes the integral transformation theorem. So it says that this expectation can indeed be written as f here. And then if you have a derivative, well, then you plug the derivative in and you're back to what you've seen in calculus. The point, of course, being that the top part here, what you have up here, this is completely general. I always have a distribution. I can always integrate with respect to this distribution function. Now, this might be very ugly over here, but it's possible to do in a lot of cases, even though you don't have a density. Okay, are there more questions or comments on this one? What you're seeing here is this integral transformation theorem. This is it is highly related to integration by substitution. It's highly related to these polar coordinates, or yeah, when you had this integral in higher dimensions where you have to compute the Jacobian. Like, this is what will take you from here to here. You have to multiply onto, there's some derivative you have to multiply onto, there's some Jacobian you have to multiply onto. And if you have a density, this is exactly that density you have to multiply onto. Any questions or comments on this before we move on to something else?
So before transitioning into this type of integral, are we supposed to be able to prove and check each one of these steps or not?
I would very much like that you could at least do this step here.
Copy that.
Yeah. Professor, I have a conceptual question, I guess. So when you went to
pause this just one time, just a little, just a little second. If I look up, let me just show you. Let me show you. I wanted to show you the textbook. I want to show you the textbook. Right. I just want to show you that it's not like out of, it's about what should we know? Yeah, I get that. But you see, if it is right here, you have a random variable and you're interested in computing this expectation, right? And you're interested in computing this expectation, but instead of integrating over omegas, you want to move it over to R. And so here's the formula that we've been talking about. He calls it mu x to indicate that this is the distribution of x. I call it f. Okay, other than that, it's the same. And you see the way that he does it is he starts out with these indicators just as we did, and then he plows through more details with how to do the simple functions and non-negative and approximation and so on. I don't care so much about these. It's always the same thing you have to do. So kind of, if you can get the basis step to work, where you do the indicator case, I would be happy. If you want to push it all the way, by all means do so. But if you're thinking about what I would ask you about, what I would expect you to know in a qualifying, not in a qualifying exam, in an exam situation, I would like you to be able to tell me, like, can you justify this formula here in some special cases? And the special case that I'm interested in is exactly this case with the indicator, right? And if you're able to do that, could ask you, okay, so how do you move on from there? But I would expect people to be able to do this, given that we talked about it in class, and given that the textbook that we're using spends 3 pages discussing this. Yeah. Okay, so then there was another question.
Yeah, I wanted to ask, when you go from the first step to the second step, right?
Yeah.
G becomes like, G in step 1 is just like 1 or 0, that
Yeah.
indicator random variable on B.
Yeah.
But when you go to step 2, it becomes like the simple function. Is that called a simple?
Yes.
Simple.
Yes, that's what it's called.
The simple what again? A simple function.
Simple function.
Oh, okay, simple function. Why is that like I don't see how that's like more general, is my
Well, at least here you can see that this G can take on M different values.
Oh, is it like a linear combination of?
That's what it is, right?
Oh, okay.
You know how to deal with these ones? You multiply the constants and you sum. These are just linear combinations
Okay.
of what you did in the previous step.
Okay, I gotcha.
And then in the third step, you take limits of such linear combinations. Positive. Yeah.
Okay, I see now. Gotcha.
So these steps here, they're more or less exactly the same as what we did last time. Like last time, we also had this way of splitting intervals. And we talked about that the nest that as n increases, these sets here, they nest each other, and you go up to, you can see here when I run them up, so I'll get 2n, and then I'll get up to m here, and this was exactly what we had last time too. And so as n increases, I get a finer and finer mesh on a bigger and bigger interval of the positive real line. Yeah, are there more questions? There was another little thing that I also forgot to tell you last time. This has come up. I think it came up last time, and it also came up in a set of office hours at some point, and it's kind of my fault. I just forgot to tell you guys about it last time. So let me just clarify that now. At some point, one of you mentioned, or multiple of you mentioned, the word null set. So let me just try to clarify what a null set is. So null sets. So they can be more. They can be more general than the empty set. They can be non-empty. Okay, let me put it that way. They can be non-empty. They can be more general than the empty set, right? So the formal definition of a null set is as follows, right? So this is the definition. A set of points, let me call them n. So this is something inside omega. This is a null set. This is called a P null set. If you can find a set M, which is measurable, such that, well, the first property is that N here, the set I'm interested in, is inside M. And the second one is that P of M is 0. Right, so as an example, we had talked about that if I looked at omega to be the interval 0 to 1, we had talked about that I could write, so pick a point pick x somewhere in there. So then we had talked about that if I were to look at the Lebesgue measure on that interval, how did we do it? We said, let me take x and then we subtract away a little bit, minus 1 over n. So I'm looking at the Lebesgue measure of the interval x minus 1 over n to x, and I'm interested in computing the limit as n goes to infinity. We did this calculation. At some point, this is going to be the limit as n goes to plus infinity of 1 over n. So this is a 0. We had a result that says that these one here, the nests, they get smaller and smaller and smaller. So if I look at the interval where I go a little bit to the left, and then I go a little bit less to the left, a little bit less to the left, and so on. So try to look at the picture. I have my x here. And so first I'll subtract away, say 1, right? So I get far down here. I get down to x minus 1 over, I don't know, 10. And then next time I'll do this one. This is x minus 1 over 11. And then I'll keep moving up. The nest, it gets smaller and smaller and smaller. And we had a property about monotonicity that if I take the limit of such nesting sets, this will be the same thing as computing just the intersection of these sets. So it'll be x minus 1 over n to x. Again, the only point, this thing here is going to keep creeping up towards x. The only point that's left in here is the set x. Right, so I get that x here, is an offset. So this thing here is a Lebesgue null set. Right, and it's not empty. So for example, if you're talking about the Lebesgue measure on the interval 0 to 1, there are lots of non-empty null sets. For example, all these single sets up with single points. Right, so from here you can also, this can be generalized, so you can get many more. But we know that so if I take 2 points, if x is not equal to y, I take these 2 points in my space, and I'm looking at the Lebesgue measure of say the union. What should I get?
Is it also a null set?
Yeah, because being a measure means that you can take the measure of disjoint unions is equal to the sum of the measure on each of the 2 sets, and the Lebesgue measure of x is 0 and the Lebesgue measure of y is 0. So this is also 0. Okay, so then I can get greedy. So what about if I take the Lebesgue measure of
a countable union of?
Yeah. So what happens if I take the Lebesgue measure of 0, 1 intersection with Q? What is that?
Just the rationals between 0 and including 1.
Yeah. And what's the measure? What is this?
It's a countable number of points, so I think it should be 0 too.
Yeah. Right. So, and this is definitely not empty, right? There are lots of rational numbers between 0 and 1. But now we can also start doing cool things. So now you can also integrate functions that you couldn't do before. You can also integrate. If I take a function like if I take a function that's equal to 1, the indicator for the interval 0 to 1 intersection with q of x. And so if I look at a picture, so it's open here, it's closed here, this is my x. If I am to plot this function here, so this is equal to 1 on all the rational numbers between 0 and 1. So I'm going to get something, it's impossible to draw, right? But this is my attempt. So now I get the idea. I want to integrate from 0 to 1. I want to integrate over omega of f of x, and then I want to integrate with respect to the Lebesgue measure. The Lebesgue measure of x. What should we get? Well, the function is equal to 1 with probability. What's the probability of being equal to 1? Well, that's going to be the Lebesgue measure of the set, right? So this thing here is equal to the integral over 0 to 1 intersection with q, and then you'll have d Lebesgue here. So this here is going to be equal to the Lebesgue measure of that set. Which was 0. Right, so if you integrate this particular complicated function, you're going to get 0. We'll try to integrate this one here. Try the Riemann integral. Any guesses on what the Riemann integral is?
Wait, this is like what's this set called again? Like the Dirichlet something.
Yeah, it's the indicator for all the rational numbers between 0 and 1. So if you try to integrate this with respect to the Riemann integral, you have to start putting lower Riemann sums and upper Riemann sums. So you're going to start trying to approximate it from above with squares and from below with squares. But this is going to be impossible because the rational numbers, you're going to be dense. So you can't get at, like when you start putting in these squares here, the lower Riemann sums are always going to be 0. And the upper Riemann sums are always going to be 1. So this is impossible. You cannot integrate this function here in the Riemann sense. But for the Lebesgue integral, it's straightforward because the Lebesgue integral doesn't see the set because it's a countable set of null sets. Yeah, so I see Rakshay, he says the upper sums get you 1, and the lower sums get you 0. Since they don't equal each other, you don't get an answer. Yeah, so it's impossible. Absolutely spot on. Very nice argument. This is impossible. You cannot integrate this particular complicated function in the Riemann sense. But the Lebesgue integral, yes, you can do it. This is fine. And then Alice is asking, can you explain why the second one is 0 as well? Is that this one here? There are lots of zeros. So can you explain why the second one is 0 as well again? So, right, if I have a probability measure, so let me just recall P going from F into the interval 0 to 1, this is a probability. Measure. If the first one is I should take p of whatever space I'm on here. So this would be p of omega should be 1. And then the second one is the one that I'm using to get this one. I'm using that the probability of a disjoint union, countable disjoint union, I can just add up these sets provided that Fn intersection with Fm is empty for any points m and m not being the same. And so here I have exactly x and y, they're not the same. So when I intersect them, I get the empty set. Then the probability of the union of these two is equal to the probability of x plus the probability of y, but we just argued that each one of them would be 0. So then we get this one. But then we're clever now, and we move over and we say, well, we can do this for countable unions. So I just take something inside 0, 1 that's countable, and then we try to do that. And so Q is countable inside 0, 1. And then I get, given that this is a countable union, probability of a countable union is equal to the sum of the individual ones, and the individual ones, they all have 0 probabilities, so this is also going to be 0. Right? But I cannot do what we can't do, that Lebesgue measure of the full thing. This is going to be equal to, we cannot do that this, we can also write this as a countable union. We can also write this as a union of disjoint sets, but the union is not going to be countable. This is not going to be summing up p of x's when x travels through the interval 0 to 1. Right? Because on one hand, this here is equal to 1, and on the other one, this is equal to 0. Right? So these are different. We cannot move away from countability here. We cannot go from n equal 1 to infinity. Right, so the party stops here. We cannot move beyond this cube, but that does allow us to integrate a function that before we could not come close to integrating with respect to the Riemann integral. There are results, so let me just show you, for those of you that are interested, there are results in here that will link the Riemann integral together with, let me just bring up the page. So for those of you that are interested in pursuing this line of argument, like in our textbook, he does have comparison results between the Riemann integral and the Lebesgue integral, and the point is that if you have a Riemann integral, then it is going to be if you have a defined Riemann integral, it is going to be exactly the same as the Lebesgue integral. However, there are lots of Lebesgue integrals that differ from the Riemann integral, simply because the Riemann integral is not defined. And so here's a specific example of it. Are there any more questions or comments on what we've been doing here?
How did you know to put the d leb when you integrated it? Like because when in calculus you think of the dx as like the infinitesimal, like very small like thing you're multiplying it by, the rectangle by.
But here it's just notation. It's just, there are many different ways of writing. Let me just bring back that sheet we had. There are many different ways of writing this quantity here. right? This here by itself is just, this is notation, right? This here by itself, this is notation. What is the meaning with this symbol here? The meaning of this symbol is that it's this supremum, which is on page 1. The meaning behind this symbol is what we have here. It's this supremum. But there are many other ways to write this. Some people write this here really as an integral. And so you will integrate over omega, and then you will integrate x of omega dp of omega. These two things, this is tomato, tomato. It's just symbols, and they mean exactly the same thing, and they mean this supremum here. Right, so what I'm doing in the example is I'm taking omega to be the interval 0 to 1, and I'm taking p to be the Lebesgue measure, and I'm taking x to be my function, that is this dotted line here. So I did nothing else than just use that notation here to write what I have here.
So you say you took P as a Lebesgue measure.
Yeah, with the Lebesgue measure on the interval probability measure, right?
Oh, okay. That's what I wasn't getting. I didn't know that the Lebesgue
right?
measure is a probability measure.
On the interval 0 to 1. Like, how long is the interval 0 to 1?
1.
Yeah, so that's a probability measure.
Okay. Okay.
But it wouldn't work on the interval 0 to 2. Then it's not that will give me 2. That's not a probability. That's why we're looking at the interval 0 to 1, because if I put the Lebesgue measure on the interval 0 to 1, it's a probability measure.
Okay.
Okay. We have 5 minutes left. There's one more thing related to these null sets that are going to come up. It's also everywhere to be found in the textbook, and it looks maybe a little bit unfamiliar, but you will see you see statements like x is equal to y. So here I have two random variables, x and y. They go from omega to r. Actually, the immeasurable functions, and you see statements like x is equal to y. You see them like almost surely, so as, or you see it x is equal to y almost surely. So sometimes you put a p here, sometimes you put a p in front. What that means is, that means that if I look at this set n, so there's those omegas, such that x of omega is not equal to y of omega, that set, this means that this set, this is a null set. This is a P null set. You often see an assumption. Indeed, it's a part of what's called so this is part of what's called the usual. It's not my wording. It's part of what's called the usual assumptions. You often see an assumption, and this is part of, there are a couple more things inside the usual assumptions, but it's part of it that says that all null sets are measurable. Right? We didn't have that assumption when I wrote down a definition, right? I'm saying that I said as an null set, if I can find something that's a little bit bigger, and then that little bigger thing is measurable. I'm not saying here that n is measurable. If n, in this particular case, was guaranteed to be measurable, we say in that case, so this here means that it belongs to F. In that case, F is said to be, and this is an unfortunate word because it has a different meaning in math finance, but in mission integration theory, they use the same word. It's called complete. So this is the word. So when you see statements like this one, X is equal to Y, P almost surely, or X is equal to Y, and then it's just written as AS. Let me see if I can find it in the textbook, and probably are some examples in here somewhere. Just so you guys can see it.
Would you please zoom out a little bit? I can now see the notes clear.
Oh, sorry. Yeah, we should move it up a little bit. There you go.
Thank you.
Yeah, so you see, here we are in, I'll put the notes back up in a second, but you can see he's starting to write stuff like this, almost surely. There's another one down here, almost surely. Right, so he's talking about the strong law of large numbers. And that theorem has this word almost surely in there. Right, so almost surely, it doesn't mean that it works for all. It means that it works for almost all, almost being measured as a set that has full mass being probability 1. So just giving you guys heads up, when you start reading the textbook, you will see these phrases at various places, almost surely. And this here is a specific meaning of it. It means that the complement set is it's a set that has at most 0 probability.
Oh, so it's saying that there are elements that where the two sets are not equal at some omega.
Yeah.
But that set is only consists of a countable number.
No. We were not saying anything about countability. We are not saying that there's no statement over here that says that all. For example, here, there's no statement here that says that all Lebesgue null sets are countable. I mean, we're going the other way around, right? We're proving that countable sets are null sets for the Lebesgue measure. We're not saying that all null sets for the Lebesgue measure are countable, and that's not true.
Okay, so there's a null set of that's not countable.
Oh yeah. Oh gosh, but now we're gonna go asking me to jump out of the deep end, but I will. So there's something called a Cantor set. Have you guys heard about the Cantor set?
Oh yeah, it's when you split it into thirds and then split it again from 0 to 1.
It's actually a very nice picture over here in the back. It's a good book. There's lots of interesting stuff in it, but it's spread around. But here's a picture that has to do with the Cantor set. This is the Cantor function. People also call it the Devil's staircase, and it is a Devil's staircase. But if you look at the Cantor set, This is not countable, but this is a null set.
Null set. Okay, it's interesting.
Yeah. So don't equate null sets with something that has a simple structure. That's not true. That's not true.
So I guess there's a pretty big almost there if there's an uncountable number of points.
Oh no, no. So now, so how many null sets are there? How many null sets? Well, there are infinitely many. I get that, but like, so we have the Borel. You look at the Borel sets, and then you look at the smallest sigma algebra that contains all the Borel sets and the null sets. Because remember, we have not demanded that the null sets were measurable, right? So there are lots of null sets that are not measurable for the Lebesgue measure. So you look at so this sigma algebra here, this is called the Lebesgue algebra. This is the Lebesgue sigma algebra. Right. And so now you can ask, how much bigger is this one? I mean, it's obviously a sigma algebra that contains this one, so it's going to be bigger, but how much bigger is it? Right, so we compute or try to figure out what is the cardinality. Are the cardinalities of these two objects the same? If they're the same, you can say that there are not that many null sets, right? Because they're going to, after all, be in the same class. But the cardinalities are different. The cardinalities of the Lebesgue sigma algebra is higher, strictly higher than the cardinality of the Borel sets. The cardinalities are different. So don't be under the impression that the null sets are simple or trivial. There are lots of them to this degree that the sigma algebras, they actually change cardinality when you include them. So the word almost surely, this people also say it almost everywhere. The word almost, I don't know if you should have picked a different word, but this is universally agreed upon to call it either AS, almost surely, or AE. This is what you will see in all textbooks. And I'm not going to justify almost being whatever it is, but I can tell you that the set of null sets is humongous, and it's so big that it breaks the cardinality. This is a bit beyond what this class is about, but you can just Google a cardinality of the Borel sigma algebra and Google the cardinality of the Lebesgue sigma algebra, and you will be able to find teaching notes about this. Okay, we were running over again, and we also are falling behind. I really want to talk about conditional expectations, but yeah, we also get into these discussions here, and I think next time we have to talk about conditional expectations. So because it's going to come in your homework, and we need these conditional expectations to be able to define what a martingale is. So this is coming next time. So next time we're going to do conditional expectations. This is going to be what we start out with, and then no more detours about all these other things. So I bid everybody a good night. I just want to remind everybody that tomorrow morning we have there is a joint office hours with another class on the same topic. So for those of you that have questions, just zoom in tomorrow morning. Otherwise, I will see you guys next week.